Hello everyone.
Our next speaker is Arabinda Behera, and he's going to talk about aging in glassy ring polymer system insight from molecular simulation.
Hello everyone. So first of all, I would like to thank the organizers for giving me this opportunity. So today I'll be talking about aging in glassy ring polymer systems. So aging basically refers to the physical aging of the system, where you have all these the physical property continue to change because the glassy systems are out of equilibrium. So first, what is the glass? So it is basically a non-crystalline amorphous solid, and so what it means that it doesn't have any regular periodic lattice pattern that you see in the crystalline solids, but and so structurally it is more closer to liquid, and it has this property that this below this glass transition temperature, the viscosity roughly goes to 10 to the power 12 pascal per second. And so so how people usually form glass, so you can do it by cooling it rapidly. So in order to avoid so you have to avoid the crystallization, and then you reach the glass state. And another way to do is to increase the density rapidly, so thereby forming a glass. So I'll be talking about the glass in case of ring polymers, or they are otherwise known as topological glasses. So what happens here is that these ring polymer systems, they are distinct from their linear counterparts, in the sense that they lack free ends, and that gives them a unique property to go through this kind of topological interaction known as threading. So what happens is that this the threading is basically one ring polymer penetrates another ring polymer, thereby restricting the motion of this ring polymer. And if they are not threaded, so they are free to move. So now the question is how you can show that this topological interaction give rise to this slowdown in system. So this was beautifully done in this work, where they showed that if you just take a particle and artificially trap the system, so what happens, what you are looking at is so there is a frozen polymer, and this only one polymer is mobile, and we track the center of mass MSD of this ring polymer, and then we see that if we do that, so what you plot here is the center of mass of this ring polymer against the time on a log-log scale. And so what you see is that this the MSD basically plateaus. So basically this ring polymer is trapped or caged, and if you do a similar treatment to a linear polymer system, but this particle always escapes. So what it means is that the topology, that is the only distinction between these two systems, is that the topology is the only thing that is responsible for the slowdown. So now the question is, can you show that without any artificial pinning, can you form a glass? So, and the answer is yes. So this was also observed in this work, that what you do is that if you increase this the ring polymer stiffness, it will form an extended structure, thereby facilitating more and more number of threading events. So, and eventually that will lead to a dynamic slowdown. Other than that, you can also increase the pressure of the system, and then you can also observe a reduction in diffusivity of the rings. And so basically, if you play with the k theta and the pressure, so you can at some level you can actually observe a glass, or you can get a glass. So now we want to ask, so what we want to do is that we basically want to ask this question: what is the stiffness effect on glass transition temperature? And specifically, we'll be interested in this k theta and theta phase diagram. And we are also interested in studying this aging dynamics below this glass transition temperature. And other than that, we will be also interested in the threading interactions in this aging regime. So now here's the simulation setup. So we have 1,000 polymers and 100 monomers per polymer, and the density is pretty high, so it's like a 0.57 bead length minus q. So, and the interactions are the monomer-monomer interactions. They interact via this WC potential, and this bonded monomers, they interact via Finney, and there is a bending potential. So what we do is that we take a equilibrated system at a very high temperature, and then quench it to a low temperature and keep the temperature fixed. So now the first thing is that we want to identify the glass transition temperature. Specifically, we want to look at the temperature versus K theta phase diagram. So what we do is that for each K theta, so we quench the temperature and then we plot this MSDs. And from this MSDs, what we can do is we can extract the diffusion coefficients and plot them against the temperature. So what you see is that if you decrease the decrease the temperature, so diffusivity will go down. And also, if you keep the temperature fixed and increase the K theta, that will also reduce the diffusivity of the rings. So that basically says that the introduction of these threading interactions, and also due to the increased stiffness of the ring polymers, that will also reduce the diffusivity. And what is also interesting is that if you just increase the K theta beyond a certain point, there is a sharp fall in this diffusion constant values. So it basically says that at a certain stiffness limit, the system is basically jammed even at higher temperatures. So, and if you feed this diffusion cost to a power law type function, you can extract this value Tc, where we expect that the diffusion will cease to exist. So, and if you plot it against the stiffness of the polymers, what we obtain basically a nonlinear curve, nonlinear dependency of the transition temperature with K theta. So, so now as we find out the Tc for each of the K theta, then we go for to study the aging dynamics of the system. So the first quantity of interest is to look at how the system relaxes as the system ages. So what we do is that we plot this intermediate scattering function, and we vary the waiting time as so waiting time basically refers to the time that I wait till I start my measurement. And so initially you don't see any effect of waiting time, because the initial high temperature effects from the following the quench that persist for a certain time. And and once the system enters into a glassy state, what you see is that as I increase my waiting time, the system takes longer and longer to relax. So, and you can feed this curve to a stressed exponential, and you obtain this relaxation time, which basically says that when this function reduces to the value 1 over e. So, and if you plot this relaxation time against the waiting time, what you see is that near to the transition temperature, if you're working close to the transition temperature, it varies sublinearly. But if you go much below this transition temperature, and then you will see that this T alpha approaches a linear dependency with TW, so which is basically known as the simple aging regime. So the next thing that we wanted to study is to look at the threading events, and we wanted to explore what is the effect of aging on threading interactions. So to do that, what we do is we define a matrix, and these elements are 1 and 0, depending on whether these polymers are threaded or not. And note that we set this PII, or this diagonal elements, to 0. So basically, we don't take any kind of any self-threading interactions. And so, and then by taking this matrix, what we do is that we define this threading correlation function. So what it basically says that it is a product of all these P matrices from 0 to till the time t. And so this basically quantifies the unthreading events that it calculates, this function calculates the time it takes for two threaded polymers to unthread for the first time. And so here is the result. So what we do is that we plot it for two different temperatures. So if you are working closer to the transition temperature, you don't see much deviation from the curve. Only at higher TW, you see that it deviates slightly. But if you just look, go much below the transition temperature, what you see is that the threading, unthreading events slow down further and further. So that basically indicates that this threading interactions are more and more persistent as you go deeper into the glassy state. So you can also extract a time scale from here. So and you plot it against the TW, or against the waiting time, and you see that it is also an increasing function of the waiting time. And also you can plot it against the relaxation time, and you will see that they are positively correlated. And so finally, to summarize, so what we did is that we observed nonlinear dependency between the transition temperature and the stiffness of the polymers. And deep in the glassy state, this this relaxation time approaches near TW, and so it is a simple aging regime. And we also see that threading events persist at much below the transition temperature. So finally, acknowledgement, and thank you for your attention.
Okay, we will have one or few questions.
Very nice talk, thank you. So I just wanted to know, like threading to unthreading, like how much feasible it is in your system. This is the one question. And the second question is threading to unthreading or unthreading to threading, the time is same or different, or how you will quantify that?
Okay, so we have not looked at individual threading and unthreading events. So of course, if they can thread unthread. So if you are working closer to the glass transition temperature, so you have more and more thermal energy. So there some rearrangements happen. So you unthread, unthread. So it basically depends on how much thermal energy you have. So and individual threading events from one threading event to other and then going back, that we have not studied.
So you have shown like this, the non-monotonic behavior of the glass transition temperature for this ring polymer, right?
Yes.
So does it has any connection with the size of the polymer, like the ring? Like why it is happening, like
So why it is happening? So beyond a certain point, so of course the stiffness actually has more effect than this thermal fluctuations. So probably that's why it is very. So at a point you can imagine that these are very rigid rings. So once you have very rigid rings, you don't have the motion is severely constrained. So that is one explanation. And with respect to size, we have not explored that one. So if you increase the size, basically what you are doing is that you also decreasing effectively the k theta of this polymer. So in that sense, so it is very complicated to answer at this stage actually.
I just have a comment. Whether the shape of the constraining system, whether you are checking this threading and non-threading, let's say in a cylinder, the space is more confined.
Okay.
So if it's in a sphere, whether it will be more, probabilistic, whether you have checked the shape of the confinement.
No, so this is periodic. Okay, all right. No, we have not looked at the confinement, so it is periodic boundary conditions.
Okay, thank you, Arabinda Behera.